Hey everyone, this is Nadeem and welcome to my YouTube channel. Today we will demonstrate about the Lenz's law. In the previous lecture, we demonstrate about the Faraday law of electromagnetic induction and we derived the expression for that. This is the final expression for the Faraday law of electromagnetic induction, and here this negative sign is explained by the Lenz's law. In this lecture, we will demonstrate about the Lenz's law. So for that we have these three operators. The one is this magnet, and this magnet have some region around this magnet in which the effect of this magnet can be felt by the test magnet. Okay, so if the test magnet is come in that region, the force will be exerted on that test magnet. Okay, so the magnetic field intensity near to this magnet will be more, and if we move away from this magnet, their magnetic field intensity will be less. And the other device for the demonstration of the Lenz's law is this coil, and this coil is actually made by the long copper illuminated wire, and here the diameter of this copper illuminated wire is about 0.2 mm in diameter, and here is about 110 number of the turns present in this coil. And we connect the one terminal of the coil with one probe of this galvanometer, and the other wire of this coil is connected with the other terminal of this galvanometer. And this galvanometer is a device which is used to detect this small current. Let's consider this side of this magnet is actually the north. So this side is actually the north. Okay. So if I bring this north toward this coil, okay, the coil will the current, according to Faraday law of electromagnetic induction, the change in magnetic flux will induce the EMF, and that EMF will oppose this change in magnetic flux. I mean that the current in this coil will be flow in such a way that this side of the coil become the north. So if I bring this north toward this coil, this side of the coil will be north. So therefore they will be this magnet and this the magnetic field of this coil will be repel each other. Okay, so they will be repel each other. So by changing the magnetic flux, the EMF will be induced in this coil, and that current will be oppose this change in magnetic flux. If this is the north, this side will be become the north. Okay, so if I bring this magnet, and this side of the magnet is the north. Okay, so this if the magnet is the north, okay, so this coil, this side of the coil will become north, and this side of the coil become the south. So if I bring this magnet toward this coil, there will be the force of repulsion. Okay, so we will bring this magnet by applying some force. Okay, so that mechanical energy will be converted into electrical energy. And here we have that same coil, but in this case we bring the magnet away from this coil. So in this case, if I bring the magnet away from this coil, okay, if I bring this magnet away from this coil, now the deflection is towards the right. Okay, here the deflection is towards the right. If I bring this magnet away from this coil, the deflection is towards the right. Okay, here the deflection is towards the right. Now in this the deflection is towards the right, And here, if I bring that same magnet with the north pole on this side away from this coil, now the EMF, due to the change in magnetic flux, the EMF will be induced in this coil, and that now the direction has changed. Okay, now this the galvanometer show deflection in this side, so the current in the coil has changed. Now this polarity will be changed, and this side will become the south, and this side will be the north. So in this case, this north and this south attract each other. Okay, so in order to overcome this attraction, we will apply the force, and our mechanical energy will be converted into electrical energy. So here I'm going to recap that if we have the coil, and if I bring the magnet towards this coil, the EMF, due to the change in magnetic flux, the EMF will be induced in this coil, and the direction of that EMF will oppose the change in magnetic flux here. So here the magnetic flux is north. The pole of this magnet is the north, and if I bring that north toward this coil, the EMF will be induced in this coil, and this side of the coil will become north, and here this north and this north will be repel each other, and we will apply some force, and that mechanical energy will be converted into electrical energy. And if we bring that same magnet away from this coil, now the due to the change in magnetic flux, the EMF will be induced in this coil, and this side will become south, and this south will attract now. This south will now attract this magnet toward itself. So we will bring this magnet by applying some force, that some by consuming some energy. That energy will be converted into electrical energy. Okay, so lens here in Lenz's law, we have the law of conservation of energy, conservation of energy, in which the energy law of conservation of energy, the energy is converted from the mechanical energy into electrical energy by such a position. Okay, so uh, this in order to overcome these opposition, we will have to apply some force, and we will have to consume some energy, and that mechanical energy will be converted into electrical energy.